Okay, in this podcast I'm talking about the introduction to the periodic table and the concept of effective nuclear charge. If you want to read along in your textbook, it's the textbook Brown and LeMay, and it's section 7.1 and 7.2. So first of all, as you probably know, this is a sort of a general format of what the periodic table looks like. Okay, when Mendeleev developed his periodic table, he took a look at all of the elements that had been discovered. He tried to arrange them in different ways to try to get some agreement around organization around properties. And he ended up putting them together basically in atomic weight order, because at the time atomic number had not been was not a concept because proton had not been discovered. And he put them together in atomic weight order, but decided where to break the row, where to start a new row, so that the elements lined up so that their properties were similar going down a group. That was the basic organization of the periodic table. If you look at the periodic table and you look at the dates down here, you'll see we said that Bohr introduced his table in 1869, right? So the elements down here that are in the purplish ones and the light blue ones had not been discovered. In addition, none of the fourth period elements that are gold had been discovered. Yet, what Mendeleev did was he left a spot for those three fourth period elements. And what he did was he gave them some names. So he said, this is Eka aluminum. Gallium is Eka aluminum. Well, he didn't know gallium, it hadn't been discovered. He said there's this element that's going to be like aluminum, I'll call it Eka aluminum. There's this element that is like silicon that I'm going to call Eka silicon. And another element that's like boron that I'm going to call Eka boron. And he did that in a way that really surprised people because, again, those elements had not been discovered. And as it turns out, what happened within 15 years of his release of the table, all three of these elements had been discovered. They were gallium, germanium, and scandium. Okay? And they fit right where he said they would, and they had properties he said. So here are the properties of Eka silicon, and this is the observed properties of germanium after it was discovered. Now this is 15 years later. Okay, atomic mass almost the same, density almost the same, specific heat wasn't quite on with color, but he knew how it would react with oxygen and what kind of combinations. He knew what the density of the oxide would be. He knew how it would react with chlorine. So really quite remarkable. He predicted an element, said what its properties would be, and in fact 15 years later that element was discovered. Okay, so give some thought to this question. Arranging the elements by atomic weight, which is basically protons plus neutrons, leads to a different order than arranging them by atomic number, which is by protons. So how can that be? Think about that for a sec. Okay, so the reason is it's all about the protons, right? Because the atomic number is just based on the number of protons. And if you're going up, you're increasing in atomic number, you're increasing the number of protons, but you're also increasing the number of neutrons. So it could be that you're adding more or less neutrons at the same time. You're not always adding one for one, right? So it's different number of neutrons being added that can change the order based on atomic weight. Okay, so we're going to talk about periodic trends. Some of those trends that we see on the periodic table: sizes of atoms and ions, ionization energy, and electron affinity. For you, if you want to get credit on the AP exam, or therefore on my exam, is that you need to recognize the difference between a trend and an explanation. A trend would say atoms on the right-hand side of the periodic table tend to be smaller or tend to have higher ionization energy. That is a trend. So when the FRQ on the AP exam asks why, and you say it's because it's on the right-hand side, you would get no credit for that. What you need to talk about is what is it about attractions and repulsions that cause that trend to be such. Okay. So we learned in the last podcast, or a couple podcasts ago, about attractions and repulsions, right? We know that the nucleus is positively charged and that each electron has some attraction to that electron that's based on the charge in the nucleus and the distance, what we call the distance r, right? It's Q1 times Q2 over r is the binding energy of those electrons. But it's not quite as simple as that, because in fact these electrons, the fact that there are multiple electrons that are the same charge, means there are also repulsions between electrons. Okay, so for any given atom, it has attractions to the nucleus, but it has repulsions to other electrons. So it's not quite as straightforward as Coulomb's, using Coulomb's law in terms of attractions. You've got to also think about repulsions. Okay, so if I take an atom and I am thinking about a specific electron, right? This electron, let's say, it's going to be attracted to the nucleus, but there are also a whole bunch of electrons in between. And because this is positive in the center and negative out here with a bunch of electrons, some of that positive gets neutralized, right? Electrons in between will cancel out that charge. So they affect how much of that positive charge the electron feels. And we call this shielding. We say that the core electrons, those that are not in the valence shell, shield this electron from the positive attraction to the nucleus. Okay. So that brings us to this whole idea about effective nuclear charge. And when we talk about effective nuclear charge, we have a nuclear charge, right? If I'm talking about sodium, and I look at it on the periodic table, it has atomic number 11, and it has 11 protons. But if I look at its configuration, it's got 2 electrons in the first energy level, it's got 8 electrons in the second, and then it's got 1 electron in its valence shell. But what happens is there's 11 protons in the nucleus, there are 10 electrons in the core. The core, in this case, includes n equals 1 and n equals 2, right? The first and second energy level. And they have 10 electrons. So 10 out of this 11 gets blocked or shielded, shields this electrons from that positive charge. Okay? So the nuclear charge is 11. The core electrons, there are 10 of them, leaving the combined effect only, this electron only feels essentially a +1 from the nucleus. And that's what we call Z effective. Z is the nuclear charge. The effective nuclear charge is what a specific electron feels. Okay, so we can determine the effective nuclear charge, Zeff, we often call it Zeff, as the nuclear charge minus the number of core electrons. Okay, so let's try. All right, so let's look at sodium. You need to understand what the electron configuration is like, right? So sodium has 11 electrons. There are 2 electrons in the first shell. There are 8 electrons in the second shell. That is a total of 10 electrons. So the electron out here only feels the 11 inside minus the 10 core, or a Zeff of +1. All right, so think about this. Which would you expect to experience a greater effective nuclear charge? A 2p electron of neon atom or a 3s electron of a sodium atom? Think about it for a minute. Okay. So this is a sodium atom, and if you think about it, the 3s electron would be right here, right? So the 3s electron is shielded by these 10 electrons inside, right? It's got a pretty large core. If you think about the neon atom, neon is the same as sodium, but we lose this outer shell, right? So the neon atom is has just 2 energy levels. So there's one of these 2p electrons, and there's eight electrons in the second period, or the second energy level. It is only shielded by 2 electrons in the first energy level. So it is going to feel much more of the nuclear pull. And so for neon, it's got 10 protons, and it's going to be minus the core, and the core is just 2. So it's going to be an effective nuclear charge is at +8. Okay, in a germanium atom, which electron will experience the greatest effective nuclear charge? Okay, and I gave you a diagram of germanium, so take a second and answer that. Okay, so the rule is going to be that the closest you are to the nucleus, the less shielding. You want to talk about less shielding. The closer you are, and an S is going to be a little bit closer than a P on this if it's at the same energy level. The closer you are to the nucleus, the less shielding, and therefore the greater effective nuclear charge. Okay, the effective nuclear charge experienced by 3p electrons in phosphorus is what? Take a minute and see if you can figure this out. Okay. So if we look at Zeff, what we say is phosphorus has 15 protons, right? That's its nuclear charge. And the inner core has 2 plus 8, which is 10, leaving it with a +5. Okay, we're going to stop right there.